Hi, this is Harder Extension 1, Inequalities topic. Just some useful relationships that you will use with the questions that you'll encounter in this topic are as follows. You'll also you'll need to know how to prove each one as well. The first one is that a squared plus b squared is greater than or equal to 2ab. Now, to prove that, we can start off with the perfect square a minus b all squared is greater than or equal to 0. We know that that's greater than or equal to 0 because anything squared is positive. It will equal 0 when a equals b. If we expand that, we get a squared minus 2ab plus b squared is greater than or equal to 0. Therefore, we end up with a squared plus b squared is greater than or equal to 2ab. Okay, so that's our first useful relationship, okay, that you should know. Okay, let's take a look at the second relationship. The second one is that a plus b all squared is greater than or equal to 4 times ab. Just be careful here. Notice that the a squared plus b squared are just individual terms there, and that's greater than or equal to 2ab, but in this one we've got a plus b all squared is greater than or equal to 4ab. Okay, to prove this one, we'll start with a plus b squared. Okay, now that is equal to a squared plus 2ab plus b squared. A plus b all squared is equal to a squared plus 2ab plus b squared, but we want to show that it's greater than or equal to 4ab. So what we're going to do instead, we're going to say that a plus b all squared is equal to a minus b squared. Now we know that a minus b all squared is equal to a squared minus 2ab plus b squared. So to make these two equal, see, this is a squared plus 2ab plus b squared. This is a squared minus 2ab plus b squared. To make these equal, I would add 4ab here because I've got a squared minus 2ab plus b squared plus 4ab gives me a squared plus 2ab plus b squared. So those two sides are equal. So therefore, we can say that a plus b all squared must be greater than or equal to 4ab. Now this is because a minus b squared is a positive number, so it will be bigger than 0. So therefore, anything bigger than 0 plus 4ab must be greater than or equal to 4ab. So that is the second useful relationship that you need to know, and it's proved using this, okay? Using the two differences of two squares. If you want, I can just expand those up here. We know that a plus b squared is a squared plus 2ab plus b squared, and we know that a minus b squared is a squared minus 2ab plus b squared, and hence, therefore, the a plus b squared is the a minus b squared plus 2ab, okay? Now, a third relationship that you should know is it's just the a plus b all squared is a squared plus b squared plus c squared minus 2 times all of these products here. Just a quick proof would be just by expanding it. If you want, the other way you could do is to actually expand it in pairs. So you could do it as a perfect square if you wanted, with two of the terms together, or you could just expand like this. I'll just expand like this quickly, where I'm multiplying a by each of those terms in the second bracket, then b by each of those terms, and c by each of those terms. You'd get a squared plus ab plus ac. Then b times each of those would be ab plus b squared plus bc. And then c times each of those would be ac plus bc plus c squared. Okay, and therefore you've got a squared plus b squared plus c squared minus, now we've got ab plus ab, which is 2 lots of ab, here I've got plus 2ab, then I've got plus 2 lots of ac, and I've got plus 2 lots of bc, there they are. And so therefore, if we want to come up with an expression like what we're trying to prove, this up here is a plus, obviously. So if you're trying to come up with that expression there, we've got that a plus b plus c squared is a squared plus b squared plus c squared plus 2 lots of So it's plus 2 lots of, so we'll just write that out, plus 2 lots of AB plus AC plus BC. Now that's that first expression, okay? And once you know that, we can just rearrange this to come up with an expression for a squared plus b squared plus c squared. So therefore a squared plus b squared plus c squared, just using this result, will be a plus b plus c squared minus 2 lots of ab plus ac plus bc. Okay, so you can just remember these two results. Okay, so we've got just the expansion of a plus b plus c squared. It's just like a perfect square, and instead of just your 2ab, if you were going to do the a plus b squared, you get your 2ab from there. Then you can think of the combination of the 2bc and then the 2ac. Okay, so I'll just fit that all on the screen for you so that you can have a look at it all together. Okay, that you may be required to prove is this: a plus 1 on a is greater than or equal to 2. To do this, you can start off with a minus 1 squared is greater than or equal to 0. And so therefore we get a squared minus 2a plus 1 is greater than or equal to 0. Now we can take the 1 to the other side and we'll get actually we'll take the minus 2a to the other side. So a squared plus 1 is greater than or equal to 2a. And now we can just divide through by a, but a has to be greater than 0 in this case. So therefore we get a plus 1 on a is greater than or equal to 2. Could only use this proof here if a was a positive number. Okay, so you need to put there that a is greater than 0. Okay, and in this last one here, to prove this, that a plus b over 2 is greater than or equal to the square root of a b, you could start with the square root of a minus the square root of b squared is greater than or equal to 0. Notice we're pretty much starting with a perfect square with most of these, okay, especially with these inequality ones here, okay. So in 1, 2, with these inequalities, we're starting off with a perfect square, okay. And with 4 and 5, we're starting off with perfect squares. So we've got the square root of a minus the square root of b squared is greater than or equal to 0, because anything squared is positive. Expanding that, we get a minus 2 root a times root b, which is 2 root ab, plus b is greater than or equal to 0. Again, taking this minus 2ab to the other side, we get 2 root ab, and now just dividing through by 2, we get a plus b over 2 is greater than or equal to the square root of ab. Okay, so these, you'll need to know how to prove all these. Now, just for some, the way that you need to think when you're doing these inequality relationships, so we need to use, there'll be the use of similarity in a lot of the questions that you do. Okay, so for example, if you are given, let's say you are given the numbers a, b, and c, which are all positive, where a, b, and c are greater than 0, or greater than or equal to 0, and you need to prove something like this. Let's say you have proven that a plus b is less than or equal to 2a squared b squared. So let's say you have proven that. Okay, now what we can do once you have proven, so let's say you prove this relationship here, and the way we read this is that the sum of two numbers is less than or equal to 2 times the square of these two numbers that are multiplied together. Now what we can do, once we've got this statement number 1, we can actually say, well, similarly, okay, we also know that a plus c will be less than or equal to 2 times a squared times c squared. And we could similarly also say that b plus c is less than or equal to 2 times b squared times c squared. Okay? What we can also do, so from 1, we can state these just by because this really means the sum of two numbers is less than or equal to 2 times the square of the numbers multiplied. So we can replace those A and B with A and C, or B and C, X and Y, anything that you want. Also, we can state something like AB plus BC, where we're not just using, we're using the product. This would be a number and this would be another number, okay? So we could also say that AB plus BC is less than or equal to 2 times AB squared times BC squared, okay? So it does not have to be, remember that AB is really just a number and BC is also just a number. So you can replace the single AB with groups of pronumerals multiplied together as well. Okay, now that's one use of similarity. Just looking at another use of similarity. Let's say you have this inequality, a squared plus b squared is greater than or equal to 2ab. And if we read this, this is the sum of two numbers squared is greater than or equal to the double of their product. Okay, so the sum of two numbers squared is greater than the double of their product. So I can just write that down. The way we can interpret this, so I said the sum of two numbers squared, which is a squared plus b squared, is greater than, I should put greater than or equal to, so is greater than or equal to the sum to, double their product. Now we could also say the sum of two numbers, so I could say, well, a plus b, so I'm going to square root each of these. So I get the sum of two numbers, so a plus b is greater than or equal to double their square root. Okay, so I have actually square rooted each of these. So I've got, instead of a squared, I've got a, instead of b squared, I've got b, instead of a, I've got root a, and instead of b, I've got root b. So if you have an expression like that, you can therefore go and write this. If you interpret it as the following, the sum of two numbers squared is greater than or equal to double their product, okay? All right, another example would be, we could say that a to the power of 10, like using this relationship here, that a to the power of 10 plus b to the power of 10 is greater than or equal to 2 times. Notice that this is like a to the 1, so the power of this is half of that, so you could write it as a to the power of 5 times b to the power of 5, just using this relationship up here. Or you could even do it from this relationship here, because the square root of 10 is a5, and the square root of a to the power of 10 is a5, and the square root of b to the power of 10 is b5, because square root means power of a half. You could also write something like this, that a squared plus b to the power of 4 now is 2 times, now I need to square root the a squared, which is a, and I need to square root the b to the power of 4, which is b squared. So using this single expression up here, we can write this, and from those we can also write things like this. So this is the use of similarity, also, and replacement of variables. So this one would be, what we're really doing here is the replacement of variables. Now you can do that, and you will need to do that at times with these problems, okay? So I'll just put that up here too, that we've got the replacement of variables. So that one's use of similarity, this is replacement of variables. Okay. Another thing that we need to look at is, with inequalities, is implications for a greater than b for real a and real b. So to prove that one quantity is bigger than another, okay, you should look at the difference of those two quantities. So for example, if you have to show, that the left-hand side of an inequality is greater than or equal to the right-hand side of an inequality, then what you should do is show that the left-hand side minus the right-hand side is greater than or equal to 0. And similarly, if you have to show that the left-hand side of the inequality is less than or equal to the right-hand side of the inequality, then you should show that the left-hand side minus the right-hand side is less than or equal to 0. Okay? Okay, another thing is if you need to show that A is greater than B, you could show that A squared is greater than B squared, or you could show that A squared, taking this B squared over, doing the difference, or you could show that A squared minus B squared is greater than 0, provided that A is greater than 0 and B is greater than 0. In other words, that they are both positive, okay? This will be really handy if the expression that you've got contains a square root or a cube root sign to use this process, okay? So if you asked to show that the square root of A is greater than the square root of B, you would show that A is greater than B, okay? All right, or if you had to show that the cubed root of A is greater than the cubed root of B, you could show that A cubed is greater than B cubed, for example, all right? So all of this is to prove that one quantity is bigger than another, that you need to look at the difference, okay? So that's one thing that you need to look at. The second thing that we're going to look at is the middle link, or the common term, I suppose, or the common link, okay? So, for example, I'll just come down here. If we've got that A is less than B, and if we know that B is less than C, then we can say that A is less than C, and that is because A is less than B, which is less than C, okay? So that's the first thing that we want to look at. So if A is less than B and B is less than C, so the middle link or the common link is the B, okay, then we can say that A is less than C. All right, another thing we can do is doing it the other way. So if A is greater than B and if B is greater than C, then we could say that A is greater than C, and this is because A is greater than B, which is greater than C, so therefore we can see that A is greater than C. So we've got those, okay? Okay, the third thing, just looking at adding and subtracting to inequalities, all right? So adding or subtracting from inequalities. Okay, now if we know that A is less than B, so if A is less than B, then we can say that A plus C is less than B plus C, okay? Or we can say if A is less than B, then we could say that A minus C is less than B minus C. So you already know that, but we're just formalizing that here, okay? So that's adding and subtracting from inequalities. So in conclusion, we can say that the direction of the inequality remains unchanged when adding or subtracting from both sides. So the direction of the inequality remains unchanged, or when remains the same, I suppose, when adding or subtracting from both sides. Okay, now for the fourth rule. Okay, the fourth rule. This is inequalities with the same direction. So inequalities with the same direction can be added. Okay, so let's have a look at that. So if A is greater than B and C is greater than D, then we can say that A plus C is greater than B plus D, okay? All right, so that's the fourth thing. Inequalities with the same direction can be added. Okay, now the fifth thing. If both sides of an inequality have the same sign, I'll just pause the video and write this out. Okay, so this one is if both sides of an inequality have the same sign, then the direction changes when taking the reciprocal of both sides. So if A is greater than 0, in other words, if A is positive and B is positive, And if we know that A is less than B, then the reciprocal 1 over A is greater than 1 over B. Okay, so you must swap signs. Okay. An example might be 2 is less than 4, so therefore a half, obviously 1 over 2 is greater than a quarter. Okay. That's so if you just can't remember that one, just remember, just try and substitute numbers like 2 and 3 or 2 and 4. 2 is less than 4, so a half obviously is greater than a quarter. Okay. And the last thing is that you don't always have to balance the sides. So you don't always have to balance both sides, just depending on what you need to prove. So for example, if A is less than B, then we can say that A minus 1, because A is already less than B, then A minus 1, which will be smaller than A, will still be less than B. Okay? Okay, because a smaller number, as I just said, minus 1 will still be smaller than that bigger number. Okay? Another thing we can write is that if A is greater than B, because A is already greater than B, then something greater than A, such as A plus 1 or A plus anything, would also be greater than B. Okay? Oops, sorry, I've just run off the screen. So if A is greater than B, then A plus 1, which is bigger than A, will also be greater than B. Okay, now I'm just going to stop this video now. So that's basically got all of the little rules that you need to know. And in the next series of videos, we'll be doing a whole lot of questions, okay? And in these questions, in the questions that you'll often have to prove a simple inequality first, and then you'll have to prove further results by using the results that you've just proven. That's often how the questions go.